So okay, so let's go back to saturation. So when we had an NMOS and saturation, and this was VDS, right? So in saturation, what is the condition for saturation?
VDS should be greater than VGS minus VT.
Correct. So VDS is greater than VGS minus VT. That's not equal to that point where it's equal, VD sat is also in saturation. So at that point, right, in the ideal MOSFET, we said IDS is given by half mu n Cox W by L into VGS minus VT the whole square, right? So in saturation, IDS is independent of VDS, and therefore we said in saturation this looks like a current source. Now in reality, however, one of the first models where we break the square law is known as what we discussed was channel length modulation. So in channel length modulation, what happens is IDS is no longer independent of VDS. So for example, if you remember the output characteristics of the transistor, right? Our output characteristics in the square law look like this. So till this point, which is your VD sat, the ID VDS relationship was initially linear, then became parabolic, and beyond VD sat it was a constant. Now in reality, however, the ID VD relationship in saturation looks something like this. That is, IDS is proportional to VDS. That is, as I increase VDS, I get more and more current, right? And so this we looked in ED is primarily because of the fact that the effective channel length of the transistor reduces. But for us in this class, what it means is essentially IDS can now be written in saturation as half mu n Cox W by L VGS minus VT the whole squared into 1 plus lambda VDS. And so again, remember, this is a model. Physically, does not have a meaning. The reason we use this model approximates the behavior of the transistor very well for most nodes, right? This term, lambda, is known as the channel length modulation parameter. Right? So what we see therefore is that the current, therefore, now if you consider the MOSFET in saturation, right? What can you tell me now? What can you tell me the model of this MOSFET would look like? What happens because of channel and saturation? What does this transistor look like in saturation?
So it looks like current dependent, voltage dependent current source.
No, so in this case, we said that here IDS is independent of VDS, right? And so we said that at the output, this looks like a current source where the current is only proportional to VGS minus VT the whole square, right? So similarly here, the way we model this, what does this mean? What does this? This continues to be the current source, but what is happening because of VDS? So because of VDS, what is happening is, if you think about the current source of the transistor, right? This is your drainage source. Now the current flowing through this transistor, unfortunately, is a function of VDS, right? So we see that we now begin to look like an imperfect current source. So what happens because of this is, this we will model it as an imperfect current source. Right? So the way we do it is we'll put in some resistor R0 in parallel with it, telling us that this is essentially going to model this relationship, right? right? And so from that you can, so what you're seeing therefore is that the transistor in saturation continues to behave like a current source. Only thing, it is not an ideal current source, but it is in fact an imperfect current source. And we model it similar to how we model imperfect current sources, basically with a resistor in parallel. Right? So let's look at some other, let's revisit some other device parameters, and then we'll come back to modeling. So let's, for example, let's do one quick question to highlight this point. So let me assume, so this is an problem, assume in saturation IDS is 1 milliamp at VDS is equal to 0.5 volts. So suppose IDS is given to be 1 milliamp, right? Question given to you is, if lambda is equal to 0.1, what is the value of IDS at VDS equal to 1 volt? What are the units of lambda? What are the units of lambda?
Volt inverse.
Volt inverse. Very good. So how do you calculate this?
So since the half mu and Cox part is essentially constant, we can just divide the two equations and we get a direct
Sure.
relationship.
Sure.
It's, I think, 1 divided by 1.05.
Good. It's very simple, right? I mean, it's basically IDS is proportional to 1 plus lambda VDS, right? So we have IDS 1 by IDS 2 is equal to 1 plus lambda VDS 1 by 1 plus lambda VDS 2, right? And so you know IDS 1 is 1 milliamp, VDS 1 is 0.5, VDS 2 is 1 volt. From that you can calculate what IDS 2 is, right? Now if I ask you the next question, what is the output resistance of this transistor? How would you calculate that? So what does the output resistance mean? That is, if I look at it at the output node, that is across the drain and source, what is the resistance, or what is the apparent resistance I see of this circuit? So how would I calculate that?
VDS by IDS.
Is it VDS by IDS or is it delta VDS by delta IDS is the question.
That's delta
So
VDS.
delta VDS by delta.
Right. So and you should remember that from here. So if you remember the ID/VD characteristics, right? So if I do ID by, so remember I'm in these two, suppose I'm in these 2 points in saturation, right? So I want to calculate what is the apparent resistance shown by this transistor, right? So therefore the apparent resistance shown by transistor, if I do ID by VDS, I'm going to calculate the slope of this line, which is not a physical line, right? If I calculate ID by VD. So R0 of the output resistance is nothing but delta VDS by delta IDS, right? So that is the slope of this graph. So that is the apparent resistance that is shown by this transistor at its output node. Are you following me? And so if I want this to be close to ideal, what should the value of R0 be?
0.
So if I want my R0 to be, if I want my current source to be close to ideal, what should the value of R0 be?
So infinity.
Very good, right?
Infinity.
So for an ideal current source, R0 should be infinity, implies what should lambda be?
0.
Zero.
Zero, right? And so now this is important. So again, if you remember the square law, when lambda is 0, things look nice and fine. Now, as I reduce the gate length of the transistor, what happens to the value of lambda? Does it increase, remain the same, decrease? If I reduce the gate length of the transistor, what happens to the value of lambda?
So lambda would increase, right?
And what is the reason behind it? You're correct. And why would it increase?
So because then the pinch off point moves closer to the drain, right?
So delta L by L, remember lambda is proportional to delta L by L. If you remember lectures in ED, right, when you're in saturation, right, your lambda is coming about because of the fact that in saturation, as you increase your VDS, you start seeing this delta L, the pinch off point moves in, right? Now, in the square law, what we say is delta L by this total gate length of the transistor is very small. And so we neglect that effect. So we say that even as VDS increases, the effective gate length of the channel continues to remain LG. Right? However, as you reduce the gate length, right, this delta L becomes a larger and larger part of your delta LG. Right? So as your gate length reduces, your LG lambda increases. And so what happens to R naught then in that case? So if my lambda increases, what happens to R naught?
So R naught will
Decreases.
R naught will decrease. So what is happening therefore is, as technology scales, as you go from node to node, as you scale down, remember all of you should be aware that transistor scaling is essentially reducing the gate length. Right? So every new node, then you work in technology, your gate length is reducing. So which means you're starting to make imperfect transistors. So today we work in the region of imperfect transistors. So R naught is a reality, you have to deal with it. So ideally for analog design, when you want current sources, you want to ensure that you find a transistor whose R naught is as high as possible as you can get. So in normal cases, when you have analog design, and this is I'm talking about 15 years back or 10 years ago, or if you work in old technologies, normally what happens is that you have a choice of lengths. So a technology will allow you to use transistors of various gate lengths. So when gate lengths, suppose tomorrow I give you a technology where I'm saying L can vary between 0.5 micron and 3 micron. So if I give you that I can support any of these gate lengths in the technology, and if I ask you, design a transistor which gives me a perfect current source, which L would you pick?
3 micron.
3 micron. Right? So remember, in analog design, generally we tend to bias ourselves towards larger lengths. Right? And the reason is because those transistors tend to be better behaved, closer to the square law than scale transistors. Now the drawback is that, what is the drawback of using large transistors? Can you think of one or two drawbacks, or at least one drawback?
So you can't fit more of them on the same chip.
Area, right? So basically, analog design therefore consumes a lot area. Now, the good part about analog design is generally in SoC design, analog by itself is a small part of design. Most of the design area is consumed by memory. So you don't have to worry about spending a lot of area on design. But it is important, therefore, to remember that analog design, there is a lot of emphasis on transistor behavior. When you do digital design next semester in ADVD, you realize that when we think about the device as a switch, optimization becomes different. Whereas in analog design, you want the entire characteristics of the transistor to be exactly what you expect them to be. Right? And so this flexibility of using large gate lengths used to be something which a design engineer had, say, even as late as 5 years back or something. What has happened of late is, as the technology scaling has speeded, what has happened is that gate lengths have gone into the sub 20 nanometer regime or 20, 30 nanometer regime. So in that regime, a technology guy will not be able to support these multiple gate lengths for you. So then you end up having problems where you have to design an analog circuit with really poor transistors. So you'll see therefore that analog design continues to be a lot in demand, because every new technology requires a new approach to design, because it might be possible that the old design will absolutely fail in the current technology. And the I would say Hence, there is a lot of demand for analog design, but also because of that, analog design is a pain in the behind simply because you'd have to be very careful. A lot of parameters need to be taken into consideration when you're doing optimization and design. Okay. So let's talk about one more parameter which will be important in analog design, which is transconductance, right? Or GM. And what is GM? GM is defined by, remember, transconductance, right? So we talk about input-output relationship. So GM is nothing but the rate of change of ID for a change in VGS at a constant VDS, right? So GM is nothing but what is the change in ID I can get for a change in VGS for a given VDS, right? And so in saturation, so again, let's assume square law, So in saturation, what is the value of GM? ID is given by half Kn prime W by L VGS minus VT the whole square into 1 plus lambda VDS. Okay. So if I want to find GM is dou ID by dou VGS at a constant VDS. Right? So the 2 comes out here, 2 cancels here, so you get Kn prime W by L VGS minus VT. So what you see here, therefore, is GM. It's important here. We look at so GM is proportional to VG minus VT. So the overdrive, and this is not known as the overdrive of the transistor. That is, it's a measure of how much the transistor is turned on beyond the threshold voltage, right? So the transconductance of the amplifier can be increased either by increasing the size of the amplifier, size of the transistor, or by increasing the overdrive of the transistor, right? And we can also substitute back for VGS by VT, and we can write GM as square root of 2 mu n Cox W by L ID. So there again, it means that suppose I have a given ID in saturation, then my GM is proportional to the square root of ID. And the third expression, which we'll all use sometimes, is, again, these are all the same expressions. The reason I'm bringing these three, and these three are very common that we use a lot in design, simply because many a times you have flexibility in choosing only one or the other. So depending on what are the circuit parameters you can change, based on that you can design the circuit used in either of these formulae, right? So again, they're all based on the same, but what you see is essentially GM, and this is again an important relationship. GM is completely controlled by what is the drive current and the overdrive, right? So so higher the drive current, you get a higher GM, right? So therefore, and why is GM important? We look at it in this class on the next. The GM is directly related to the gain of the transistor, right? So you normally, if you want a particular signal gain, you want to go with a transistor which gives you a high GM. And so you can get that high GM by either increasing the size of the transistor or by pushing a lot more current through the transistor. Okay. So for completeness sake, we'll also talk about body effect.
So could you show the slide once more?
So how did you get the second equation for the transconductance?
Substitute VGS minus VT, substituted from the IDS expression, remove 1 plus lambda VDS. So many a times in this class, what we do is we will not use this for more. So what happens in most of the time, lambda VDS is going to be much smaller than 1. So we're going to neglect that with respect. To the other terms when we do the DC analysis. I'll get you. We do all that when we do examples in class. So when you're going from this expression, basically replace VGS as VT as a function of ID, removing these lambda VDS term, and then you get these two.
Okay, sir. Thank you.
Sir, I have a question. So would you say that the transconductance is directly proportional or indirectly to VGS minus VT?
Hold on to that. So it depends on what is the constant term. So that's why I said you, depending on what is constant, you base it off that. What are the freedom degrees of, see, design is all about, you have certain degrees of freedom and you have to pick two, right? For example, many times what happens is you will have the option of changing the VGS minus VT, say, using some other voltage technique. So in that case, then you'll have to pick what is the right VGS minus VT for a given amplifier gain, right? So there you can pick either using the first formula or the second formula. Whether you pick one or the other will be dependent on, okay, what is the ID you can tolerate? Say I gave a power envelope to you, then that will give you a maximum ID. So then from that you can back calculate and see. When you do more examples, you'll understand. Right now, I'm just giving you the different expressions. When you start doing design, you'll start developing the intuition as to what to use where.
Okay, sir.
Can I go to the next slide?
Yes, sir.
Okay.
Yes, sir.
Okay, let's talk about body effect. Right. So remember, in reality, a transistor has four terminals, right? We have the gate, source, drain, and we have the body terminal. And if you remember in your transistor cartoon, right? So normally in most cases, we will ground the body and substrate together. So in most cases, substrate and body are tied together, in which case you don't have an issue. In the case where the body and substrate are not tied together, then you end up having a change in VT. So if there is a bias present between the source and body, you get a change in VT. So the new VT is given by VTH at 0 plus gamma times square root of 2 phi f plus VSB minus square root of 2 phi f. Right? So remember this expression, all this means is that in the cases where your source and body are not tied together, you have to model that using a change in VT. Right? And this term is known as the body effect parameter gamma. Typically, it's 0.2, 0.3, so 0.2 to 0.3, and the unit is square root of 4. Again, we will not obsess ourselves too much in this class because we're doing the first class analog design. But when we do ADVD, we will come back to this. So remember that in most cases, either we will ignore the body effect in case the body and the source are not tied together. So we'll assume that gamma is equal to 0 in that case. Or we'll always assume that the body and substrate are tied together, source are tied together. Right? So in this class, you don't have to worry about the effect of gamma. But remember, in reality, gamma is a real effect. Right? Now, again, impact of gamma is important in planar transistors. When you start working in FinFET and nanowire and nanosheet designs, then body effect doesn't exist in fully depleted devices. So again, this is something which is vestigial of the long channel planar transistors that we've had. And hence for completeness, I've put it here. But again, in FinFET designs, we won't really use this. So in the real world, you're not going to be using this most of the time.
Sir, I have a doubt.
Yeah.
Like, why would you risk having a current flow from source to body? Is my doubt. Like, why even bias it if you are going to run into?
No, it won't. It won't be a question of biasing. Many a times this is dictated by layout. So I think for that you have to do a VLSI design class. So once you do a VLSI design, when we talk about layout, etc., then you'll begin to understand why there is a bias between the body and substrate. It won't be real clear right now if I just draw the circle. Ideally, you don't want that, but many a times you have to live with that because that's how, unfortunately, layout works. So it's more of an unwanted effect. Now, people have figured that like 20 years ago that we can use this to electrically change the VTH. So a lot of digital designs, we use this to modulate VTH. But again, all this, last 5-6 years, nobody uses this in FinFET models. But so in the old technologies, people continue to use it. But in none of the latest technologies, we don't really worry about the body a lot. Okay. The last thing I want to remind you guys about is subthreshold conduction. What I mean by that is, when VGS is less than VT, right? We essentially said that IDS is 0. In reality, that is not the case. IDS is a small quantity. So if I plot log of IDS, should remember this from ED. If I plot log of IDS is a function of VGS in semi-clock plot, what I see is that the graph looks something like this. That is, the current IDS drops logarithmically, exponentially drops as you reduce the voltage from VT all the way down to 0. And beyond VT, you guys know the model. It's either a square law or a linear relationship, right? And so this whole thing, right? We are essentially modeling this. In reality, we're just modeling this as a step function here. So if you look at all the models that you're using in this class, we are saying that at any gate voltage below VT, there is no current flowing. So we are grossly underestimating what is the power consumed by the power supply when the transistor is cut off, right? And so many a times, again, that is something important, especially as you scale transistors. What happens is that the subthreshold slope becomes worse and worse. So these things are important in current design. So when you do a full-fledged design, it's important to worry about what happens in subthreshold. How do you ensure that the subthreshold conduction is minimum? How do we ensure if we have to arrest for it, and we need to have some switch transistors to arrest for it, etc. So there are a lot of techniques available in design to reduce the impact of subthreshold. Again, those are things which we will not do in this class, again, to keep it simple. But as you take advanced classes, these concepts will come back in as you start to do design and start to make your design better and better. Okay. So those are things I want you to remember. Again, we will continue to use the square law. So we will not diverge much from the square law. But these are things to keep in mind about the limitations of square law. The square law, and again, unfortunately, because this is an online semester, we're not doing cadence with you. But when you do cadence, you'll realize that the square law model is a good place to start. It gives you a good starting point for design. But eventually, design needs to go using the right SPICE models. We go and then develop further off the square law. The square law, therefore, gives a very good starting point for design. And then you go in and optimize it further. So unfortunately for you guys this semester, you'll just learn the square law, you learn how to do design, how to find the starting point. If you guys are back next semester, then maybe in ADVD we can think about how to teach you optimization further. Okay. So let's now talk about large signal models, which is what we've been doing so far. So if I have an NMOS, right, connected in a circuit where we know that this transistor is in linear region, right? That means we have the condition that VDS is much smaller than 2 times VGS minus VT. So if I have something like this, what does this mean? What does this transistor look like in the output? When I have it in linear region where VDS is less than 2 times VG minus VT, what does this mean? How do I model a transistor?
A resistor.
Right? So the way you'd model this, and this is known as the large signal model, is in the circuit, I'll replace the transistor with the circuit which looks like this. Now this is the source node, this is the gate node. Right? So I will replace this transistor with the circuit which looks like this resistor circuit, whose R on is proportional to 1 by VGS minus VT. Right? And so when I want to solve them, if I have other resistors, other capacitors, etc. in the circuit, once I know what region of operation the transistor is, then all I do is replace that transistor in that circuit with this model. And remember, this is a large signal model. We'll next talk about small signal models, and then the things will be different. Similarly, if the transistor is in saturation, how would the model look like? So suppose I assume the transistor in saturation with VDS greater than or equal to VGS minus VT. How would the model look like?
Sir, ideal model would be like current source, ideal current source.
Correct. So the way you would again draw the model is, this is your gate node. You have a common source node, right? And the ideal model would look like this. There is a current source. ID SAT, right? So this is your model for the transistor when there is no channel length modulation. In the case of channel length modulation, it is going to be N or not W. So this is how your transistor looks like when you are thinking about the transistor and you want to solve circuits based on that. Now, why is this important? Now, this will be important because in this class, so again, remember this ID SAT is proportional to VGS minus VT whole square, right, in our model. Right? So we have a current voltage dependent current source, which is what we've been talking about. Why? So in this class, what we are interested is, we are going to be basically working on amplifiers, or what are known as small signal models. So we will first learn how to bias a circuit. And once we learn biasing, then we learn how a circuit works as an amplifier around the bias point. So before we go any further, let's solve a problem related to this. So let's.
So could you go to the previous slide?
Sir, here we are modeling as imperfect. Are you taking into consideration the channel length?
Right, channel length modulation, then we'll model it as an imperfect current source, else we'll model it as a perfect current source.
Okay, sir.
So could you go to the previous slide?
So there's one thing I don't understand. Like the variable over here is VDS, right?
Where VGS, no? This is IDS VGS.
No, not in this graph, in the transistor model that we have just done.
So somebody wanted to look at this. Let me first finish that.
Thank you, sir. I'm done with this.
Yeah, go ahead, Anand.
No, so I was asking, in this circuit, the variable, the ones that are constant are VGS and we are varying VDS, or is it the reverse?
No, that depends on how we're going to do the circuit. So this is just how we'll think about the transistor. Now, what varies depends on what the external circuit is.
Okay, sir.
Let's do a question. Let's do an example. So I want you to plot I versus V1 in the circuit below. Assume lambda is equal to 0. So this is my circuit. So I want you to plot I1 versus V1 for this circuit. That is, so basically you want to plot this graph. It's a very simple circuit. How would the relationship between I and V1 look like?
So for positive values of V1, I will be very close to 0.
Okay, and so how would the graph look like? So what happens if V1 is negative? So let me also make it easier for you. Let's assume V1 is greater than or equal to 0. So just plot me in the first quadrant.
So when V1 is negative, we can assume the V1 terminal to be 0 and VDD is equal to minus, the modulus of V1.
No, so don't worry about it. I'm saying V1 is positive. Plot I1 versus V1 for me. How does the graph look like?
Sir, in this is the body forward biased because it has a positive terminal voltage.
The body and substrate are shorted. They're the
Okay,
same.
yeah, correct. Yes, thank you.
There's no current flowing due to accumulation.
There's no current flowing because of accumulation. Where is accumulation?
Because V1 would be higher than VDD, so
Who says
there's no
V1 is
channel.
higher than VDD?
Sir, if V1 is 0, then we would have essentially the transistor is current will flow in the transistor. Eventually, as we raise V1, it will go from being in saturation to being in the linear region, right?
No.
Since V1 is a source voltage.
No. Okay. Anybody else? So how does the graph, anybody want to comment on the shape? How does the graph look like? Is the current valid for all V1? Does the current become 0 after some V1? Does the current remain 0 below some V1? How does the graph look like?
What?
Okay, let's start again.
Below V1, it will be quadratic.
Below what?
Below a certain V1, so that VGS minus VT should be less than VDS.
Okay,
sorry.
and what happens beyond?
Then it should become linear. No, beyond I'm not so sure, but
No, you guys should be very sure about this. This is one of the simplest. We will give you much more complicated circuit science. So let's work together. Okay. First, let's identify the region of operation of the transistor. Okay. Let's assume that there is some V1 applied at the source. So what is the value of VGS for M1?
So VDD.
VDD minus VGS, right, between gate and source. So what is the value of VGS?
VDD minus V1.
VDD minus V1. What is the value of VDS?
So VDD minus V1.
VDD minus V1. So if VGS is equal to VT, what region of operation is the transistor in?
Saturation.
So first thing is, because VDS is always greater than VGS minus VT, right? Transistor is in saturation, right? So first thing, therefore, is that at no point is the transistor going to go into linear region, right? The transistor is always in saturation region. Now, at what point will the transistor go in? So the only other, so we know that a transistor is in saturation for some value of V1. Now, as I keep increasing V1, what happens to this term VDD minus V1? So let's assume VDD is some 5 volts, right? So if I keep increasing V1, it starts in VDD minus V1 keeps dropping, right? And so eventually what will happen? When VGS falls below VT of the transistor, what happens to the transistor?
Cut off.
Right? So when VGS falls below VT of the transistor, what happens to I1 goes to
0.
0. And at what point does VGS become equal to VT? VGS is equal to VT means VDD minus V1 is equal to VT, implies V1 is equal to VDD minus VT. Right? So when I suppose I start at 0, right? Current. So now let's plot. So we know current is in M1 is in saturation, right? So if M1 is in saturation, I1 can be written as half Kn prime W by L VGS minus VT the whole square. VGS is nothing but VDD. So VDD minus V1 minus VT the whole square. Okay. So this equation is what will determine I1 versus V1 as long as the transistor is in saturation. So the transistor goes into two states, saturation and cutoff. So we know that the transistor goes into cutoff at VDD minus VT. Right? So at all voltages beyond VDD minus VT, the current is a constant at 0. Now therefore, when is the current going to be maximum? The current is going to be maximum when V1 is equal to 0, right? When V1 is equal to 0, the current is maximum. As V1 keeps increasing, this current keeps dropping quadratically. So the way your IV relationship is going to look like something like this, where this is Imax, and Imax is given by half Kn prime W by L VDD minus VT the whole square. Right? So this is how your relationship between I1 and V1 will look like, right? So anytime when you have to think about a circuit, the first thing you have to think about is what is the region of operation of the transistor. Right? Figure out what are all the different regions. So the first thing we always do in questions like this is figure out what the region of operation of the transistor is as the voltages vary. Right? Once you identify those, then it's quickly a matter of just putting in these expressions and finding the relationships. Right? These are approximate graphs that you want to draw. Right? So again, what you see here is when you've connected this voltage to the source, right, of the transistor. So essentially, as you're pumping the source up, eventually the transistor is going to shut down. Any questions here?
So what if V1 is less than 0?
You tell me, what happens when V1 is less than 0?
It goes beyond Imax.
It will, no? What happens to the value of Imax? Imax keeps increasing, right? So it's going to have a relationship like this. Right? Because as your V1 goes down, you're essentially increasing your VGS, right? Suppose your V1 becomes negative. Suppose VDD is 5 volts and V1 becomes minus 1 volt. Then your VGS actually becomes 6 volts, right? So its current should be higher than when V1 was 0. Right? So one way to increase VGS is make the source more and more negative. As you make the source negative, VGS in fact keeps going higher, right? Any questions? We'll do a couple.
So it is VDS is VDD minus V1, right? Okay.
V1, yeah. So we'll do a couple more questions in the tutorial next week, but this is an important concept you have to learn, because if you don't, you have to first figure out how you're going to bias the circuit. So it's important to understand how to bias the circuit. So for that, you need to learn the relationships between the various currents and the voltages that have applied in the circuit.
Sir, could you explain the I equal to 0 calculation?
I equal to 0, okay. So let's put some numbers into this, okay? That will make maybe your life easy. So let's say 1 volt VT, and let's say Kn prime W by L, whatever, right? Let's say that is 2 milliamp, right? Right. So these are my values, everyone. So first of all, all of you should be convinced that this transistor is always in saturation. So whenever you tie the gate and drain together, that is when you make VGD 0, when VGD is 0, then transistor is in saturation, right? Right. And the reason why we call this the drain and not this the drain is because the voltage is higher at this end. So now when VGD is 0, transistor in saturation, so at any point, I1 is given by half Kn prime W by L VGS minus VT the whole square, because I said lambda 0, right? Half Kn prime W by L is 2 milliamp, so half this becomes 1 milliamp. So 1 milliamp times VGS minus 1 the whole square, or it is VGS minus 1 the whole square, right? Now what is VGS? This is gate, this is source, this is drain, right? So VGS is given by VG minus VS, right? VG is nothing but 5 volt and VS is nothing but V1, right? So VGS is 5 minus V1, right? And so therefore your I1 is written as 5 minus V1 minus 1 the whole square, or 4 minus V1 the whole square. So therefore you see that I1 reduces as V1 increases, and it reduces in a parabolic fashion, right? So if I plot I1 versus V1, it's going to do this, right? Now the question is that, is the transistor always in saturation? No, the transistor gets out of saturation when VGS becomes equal to 1 volt or equal to VP, right? Anything below that point, the transistor is in cutoff, and when transistor is in cutoff, then transistor is in cutoff. And what does the cutoff mean? Cutoff means that I is equal to 0, right? So when the transistor goes into cutoff, then the current flowing through the transistor goes to 0. And when does the transistor go into cutoff? The transistor goes into cutoff when VGS is 1 volt. What is VGS? VGS is 5 minus V1, and that should be equal to 1 volt. Implies when V1 is equal to 4 volts, then transistor is in cutoff, right? So for any voltage, when V1 is any voltage equal to or greater than 4 volts, then VGS becomes less than 1 volt. And since 1 volt is your VT, that essentially means the transistor is cut off. So there's no current flowing through this circuit when V1 is greater than 4 volts. Right? And so essentially what that means is that this current is going to be parabolic till it hits the 4 volt. And at that point, the model changes and it becomes a pure 0 current, right? And so now if I look at the value, what is the value at V1 equal to 0? It is 16 milliamp. Right? So 16 milliamp falls to 0 milliamp within a span of 4 volt voltage. Is that clear now?
Yes, sir.
Okay. So let's. I was hoping to start small signal modeling. Let me take a couple of minutes and let me just get you started on thinking about small signal. All right. So what are we going to do in this class? So in this class, as I told you, we're going to worry about amplifiers. Right? And so what are we doing in amplifiers is we always have a small signal, which is an AC signal. Right? So in other words, we'll have say a 1 millivolt or a 10 millivolt signal, and we want to amplify that signal. So many a times at any voltage at any point in the circuit, you will have a DC voltage and you'll have a small signal AC voltage in the signal in the circuit, right? And we are interested in understanding how this small signal moves through the circuit. So eventually we want to design an amplifier. We want to track this small signal as we look at the various nodes in the circuit. And hence we want to see eventually if we can amplify the signal, right? So many a times, therefore, in small signal, we have to worry about a small variation on top of a DC voltage. For example, suppose if I plot this voltage, when you say, for example, I have a node whose DC voltage is 1 volt, right? So as a function of time, how does, and suppose I have a 10 millivolt sine signal riding on it. So essentially, my signal that is going to look in reality in the circuit is going to be a 1 volt signal with a 10 millivolt signal riding on it. So this is nothing but 1 volt plus 10 millivolt sine omega t, right? So what is the, if that is going to be some voltage V1, what is the maximum value of V1? V1 varies essentially between 1.01 and 0.99 volts, right? Now what we are interested in, not so much, so once this 1 volt is fine. Now suppose I increase the, something happens in the circuit and I'm able to increase the AC voltage to 20 millivolts, right? So what I'm interested there, V1 will then become 1.02 to 0.98. Right? So what I'm going to be interested is not necessarily the DC voltage, right? But rather I want to see how the AC voltage moves through the circuit. So in that case, we're going to talk about not only the large signal model of the amplifier, we're going to talk about small signal models of the transistors. That is, if you think about a transistor which is biased, say I've biased it with some VDS, with some VGS, right? And some IDS is flowing through. Now suppose I apply a small signal on the gate voltage. In addition to this DC voltage, I'm interested to know how does the small signal affect the current that is flowing through the transistor, and how does it affect the output voltage of the transistor, right? So the large signal model relates IDS as a function of VGS and VDS. Remember, I'm doing all these with capital letters and capital subscripts, right? So this is the DC model, right? Or the large signal model. What we are now going to develop in the next class is I'm going to develop this IDS, which is going to be another function of VGS and VDS. So here I'm going to develop a model where I just want to look at the AC parts of what is happening around the transistor. And this is known as the small signal model. And what we'll find is that the small signal model is nothing but a linearizing this large signal around the bias point. So what we do is this. So what we're doing is a small signal model linearizes the circuit around a bias point. So we'd be interested in two things, therefore. The model, therefore, becomes a function of the bias point. And this is basically the crux of design, in trying to understand how you're going to bias the circuit, and then based on where you're going to bias, the circuit properties are going to change. So not only you worry about the transistor sizes, the voltage sources and all that you're applying, you also have to worry about how are you biasing the circuit. So we'll spend a lot of time in this class also talking about biasing circuits. How do we bias how do we bias these circuits? How do we bias these amplifiers so as to get the required gain or the required properties of the amplifier? Okay. And this is why, again, in your entire course structure, we spend a lot of time talking about, in fact, this semester, all you guys will be talking about is LTI systems, linear time invariant systems, right? Across control systems, across signal systems, and microelectronic circuits. And linearization is a very important concept. Unfortunately, linearization is about which we can formalize a lot of design and formalize a lot of theory. Anything beyond linear becomes hard to formalize and do back of the envelope calculations. So hence you'll see that in your course structure, in general, when we model things around us, we limit ourselves to linear models just because they're easy and they give a good starting point for us to understand what's happening around and to replicate it, which is the whole point of engineering. Okay, so I'll stop here. We'll start with small signal model in the Monday's class, and then we will look at what is a bias point, how does an amplifier look like. Okay, so Yeah,
Like,
go ahead.
do you understand what you mean when you say large signal? And like the amplitude is large, but how does it affect why you have different models?
We'll talk about it. Wait, give it a few more classes.
So can you show the first slide?
Also, sir, like I don't understand this IDS in a DC model is a function of capital VGS, capital VDS. You're assuming them to be constant DC